Alright, let's go over some calculating heats of reaction questions. Starting number 1. What is the standard heat of reactions, delta H of F, for the decomposition of hydrogen peroxide? We have an equation given here. And here's water, hydrogen peroxide, carbon dioxide, and hydrogen gas. Alright, and it gives you the values of delta HF for water, for hydrogen peroxide, and carbon dioxide. Alright, so based on an equation here, that delta H degree of F is equal to the sum of, the sigma sign sum of, times the moles of the um, change in enthalpy of the products minus the same thing, change in uh, enthalpy for the reactants. Alright, so then we have to calculate this. We always have to recognize that single elements on its own have 0. So the value of delta HF for this is going to be 0. So we know this is 0, and we're given all the other values. So the products, we have to look at the arrow sign. We look here. So we have 0, delta H, F equals, we have first CO2, and we have a 1 in front of the CO2. 1 times, 1 times, and then the value for CO2 is negative 393.5 plus, and then we have 4 times, and then we know that the value for the single elements on its own is always going to be 0, so it's 0. And then we have this minus, since it's product, we have to minus the reactant now. We look here, we have a 2, so we have 2 times, the value of H2O is negative 241.8 plus the value of CH4 is 1. There's a 1 in front, invisible 1. 1 times the value of CH4 is negative 7.4.86. Alright. So when we solve this, here we have 0 plus 0 essentially. So we have 395, or 393.5 minus the value of 2 times negative 241.8 plus minus, so essentially you get 2 times negative 241.8 minus 74.86. That will give you negative 558, negative 558.46 as your answer. So then all you got to do is subtract from this. So this is subtract, makes it an addition. So you're adding negative 393.5. You're taking negative 393.5 and adding 558.46 to it. And that will give you your final answer of 164.96 kilojoules per mole. All right. One key thing to note is that kilojoules per mole is equal to kilojoules because the kilojoules is assumed that it's over 1 mole. So it's actually over 1 mole, but we don't put that because the value of 1, the mole is 1. So looking at this, is our answer positive or negative? It is positive, which means that it's going to be an endothermic because heat enters. If it was an exothermic, it would be a negative because heat left. All right. Second question. Calculate the standard change in enthalpy, delta HF, for the following reaction using the table. We have iron Fe2O3, we have CO, we have Fe, and we have CO2. We have to recognize that Fe is a single element, so it's going to have a value of 0 for delta HF. All right, we have a graph, we have a chart of all the values. We're going to find Fe2O3, Fe2O3, 3CO, so it's CO. CO is here. And Fe we don't know because, or we know because it's 0, and then CO2 is right down CO. So these are the values that we're going to use. Same thing as number 1, we're going to grab our equation, delta HF equals product minus reactant. So we take product, parentheses, we have a 2 in front of the Fe, 2 in front of the Fe right here, times we know it's 0, plus the other product, 3, times CO2 we figured out was negative 393.5 on the chart, minus the reactant, which is 1. There's a 1 in front of the imaginary 1 in front of the Fe2O3, so it's going to be 1 times the value of Fe2O3 is negative 822.1 on the chart, plus the value of 3 times the value of CHO, which is negative 110.5, and solve. All right, 2 times 0 is 2. 3 times negative 393.5 will give you negative 1180.5, and then minus, and then this will give you a value of negative 822.1 plus 3 times negative 110.5, which gives you negative 1153.6. Once again, subtraction means addition, so you're in fact doing negative 1180.5 plus 1153.6. All right, and so then we'd bring it down and we solve this and plug it in our calculator, and our value for delta F is going to be negative 26.9 kilojoules per mole. And that is our final answer. And as we said, kilojoules per mole is kilojoules, regular kilojoules. And if we were to put this into a thermochemical equation, we would just realize that it's exothermic because heat left, therefore it is negative. So it would go on the product side because the heat is leaving the system. Vice versa, if we looked at question 1, where it's a positive value, there's nothing in front of the negative, or there's no negative in front of the 164, then we would know that it would be on the reactant side because he has entered the system. All right.